So let's pick up with cardiac auscultation, and let's just start with the definition for auscultation. Auscultation is the act of listening to sounds within the body. We typically think of a stethoscope on a chest to listen to heart or lungs. So in those cases, we're talking about a cardiac auscultation if we're listening for heart sounds. We're talking about pulmonary or lung field auscultation if we're listening to the lungs. Perhaps we're listening for crackles, rales, indication of a compromised airway or pneumonia. But it doesn't even have to be just those two. We can also listen for GI sounds. We can listen for gurgling and GI movement, or a term called borborygmus. We'll talk about that when we get to the GI chapter. So just remember that auscultation doesn't have to be heart. It's just the act of listening to sounds within the body. There are a first and a second heart sound that we'll talk about predominantly. The first heart sound is called lub. The second heart sound is called dup. Lub is created by blood turbulence associated with the AV valves closing. So as those valves close from the atria into the ventricles, we're going to get blood turbulence. The lub is not the slamming shut of the valves that you're hearing, but it's actually the blood turbulence. Same thing is true about that blood turbulence when we talk about the dup heart sound. It actually is a representation of the turbulence that occurs when the outflow or the semilunar valves close near the end of ventricular systole. There is, I believe I put a link in Canvas. If not, or if it's not working, try and do a search for the University of Washington Department of Medicine Heart Sounds tutorial. It's worth a listen. They use it for their medical school students, and it's actually worth a listen just to get a feel for those sounds. Um, this video is going to be vocab heavy, and you really need to understand the relationship between the terms that we're going to talk about. Remember that we defined stroke volume in our last video using end diastolic and end systolic volume. We're going to use that value for stroke volume now, and we're going to use it to talk about total cardiac output. So that stroke volume is the amount of blood that got ejected from the left or right, but we really talk about the left ventricle with every contraction. Cardiac output is that amount of blood, the stroke volume, multiplied by the heart rate. So in a resting male, cardiac output is going to be about 70 mils per beat. At 75 beats per minute, we're going to come out with roughly 5.25 liters per minute. On average, a person's entire blood volume flows through the pulmonary and systemic circuits each minute. You'll remember that because we talked about the fact that it takes a red blood cell roughly a minute to make it through the whole cardiac cycle. So in any given minute, everybody is moving, and it takes roughly a minute to move an entire blood volume through the pulmonary and systemic circuits. Cardiac reserve is another term. Cardiac reserve talks about the difference between your cardiac output at rest and your cardiac output at maximum work. Okay, so how much cardiac output can the heart generate if it's working at its hardest? So very simple subtraction problem. Cardiac reserve is equal to the cardiac output at max activity minus the cardiac output at resting. Average cardiac reserve is about 4 to 5 times the resting value. Athletes, it'll be higher. They have more efficient hearts, so that cardiac reserve will be about 7 to 8 times the resting value. Persons who are compromised with severe heart disease have little to no cardiac reserve. They don't have a significant difference between what their heart can do resting and what their heart can do at maximum volume or maximum work. And that is part of why we see the clinical signs that we do with cardiac disease. We can affect cardiac output. We can affect it by changing the stroke volume. So the total volume of blood being moved, and maybe that's a function of the efficacy of the ventricular contraction. Maybe it's a result of blood volume. We can alter cardiac output with heart rate, or both, a combination of the two. But in and of itself, please disregard that page number. I think it's from an old version. There are three important factors that can affect stroke volume. One is called the preload. It's the amount of blood that fills into the ventricle before contraction. The second factor is the contractility of the ventricle. How efficiently do those contractile fibers actually contract? And the third important factor that affects stroke volume is the resistance in the blood vessels, the aorta predominantly, or even the valves, the aortic valve. So when the aorta is damaged or has plaque or is compromised in some way, or the valve, we have an insufficiency, or we have a compromised valve, then the heart is going to pump, but we're going to have resistance, and that resistance is called afterload. So you have preload, you have the actual contractility action, and then you have afterload. So remember that we said that cardiac output is affected by changes in stroke volume and heart rate, or both, that we have three important factors: preload, contractility, and afterload. Preload is the stretching. How much stretch do we get on those cardiac ventricles? How much blood can fill into that space? We'll talk on the next slide about Starling's law of the heart, but basically the more the heart muscle is stretched, the greater the force of contraction. By increasing preload, increasing the stretch, more blood into the ventricle, we're going to increase stroke volume. Contractility is going to rely on those autonomic nerves that we haven't fully talked about yet, but will. It's going to rely on hormones. It's going to rely on calcium and potassium levels, how well those fibers are depolarizing and repolarizing, and what kind of contractile force we're getting. Afterload, again, is resistance. It's that amount of pressure created by blood in the way of the blood attempting to leave the ventricle. High pressure is going to create a high afterload or a high resistance. So the more resistance, the more we're going to see a decrease in the stroke volume. As promised, here is the drawing or the diagram, the graphing out of Starling's law. And essentially what we're looking at here is the more we increase preload, or muscle stretch, the more blood that's in there, the more forcefully the heart contract. So it's like a rubber band. If I stretch that rubber band further and let it go, it's going to shoot farther or have more force than if I only stretch it a little bit. Starling's law is really a result of stimulation by the sympathetic nervous system during exercise. So it's going to increase venous return to the heart. We're going to see more stretch on that heart muscle, and we're going to see an increase in cardiac output. I'm not, oops, sorry about that. I'm not 100% sure. I'm pretty sure this came from the textbook. It might have actually come from maybe another book, Tortua or somebody like that, but I really like it because it's a nice summary slide of what happens to cardiac output when I do these things. So all of these are methods for increasing cardiac output. We can do it through preload, through contractility, through decreasing afterload, but in any of those three instances, what we're doing is we're increasing the stroke volume, and anytime I increase the stroke volume, I'm going to increase the cardiac output. Down here, I can have a nervous system input. We can have a chemical input like catecholamine or thyroid hormone, or even other factors. Maybe you're an infant, you're a senior citizen, you have, different body temperatures, those sorts of things. And what we're going to do is we're going to increase heart rate. Again, anytime we increase heart rate, we're going to increase cardiac output. So I like the summation of this slide. We're going to go ahead and halt here. We're going to pick up with regulation of heart rate and start talking about how the sympathetic fibers, how the central nervous system can influence heart rate.